Hello, everyone. This is Sarah, and this is episode 6 of my ongoing battle to make CSS less of a dumpster fire to work with. To contextualize where we came from at the beginning of the quarter, we recently developed a tool called Ply that allows users to perform basically runtime checking of individual CSS styles on a page, determine whether or not that those properties actually have any impact on the visual outcomes on the page, and then hide all of the ineffective properties from the inspector, which in many cases decrease the amount of properties that they had to wade through to find the relevant code quite significantly. This quarter, we wanted to turn our attention to kind of a bigger problem, which is how do you teach the semantics of CSS, which in many cases are extremely complex, to people? And the kind of high-level insight is that although CSS seems very simple and has, say, a finite number of properties, and each property in many cases a finite number of value types that are allowed, a lot of those properties and effects are combinatorial, both between individual properties where put together they have an effect but separately they don't, and across elements. And we'll see some more specific examples of what I mean by that in a bit. There are kind of two big problems that motivate our particular line of work. And the first pertains to the intrinsic semantic complexity of CSS itself, coupled with the lack of formal infrastructure that exists to develop tools around those semantics. So for example, CSS does not have an EBNF grammar that specifies the allowed values for any individual property. So an example of that is the position property can be assigned a value of static, which is default, absolute, relative, none, fixed, so on and so forth. Each of those values has has obviously a different effect on the page that's interpreted by the browser rendering agent, but there's no formal place in the spec writing process that outlines what the EBNF grammar for the whole language is, which means that the spec, which is a natural language document written by humans in the CSS working group, it's possible for the spec to refer to values that haven't been defined anywhere else, which obviously makes it very difficult to automatically reason about CSS as the CSS model. And then we might want to think about the dependencies between properties. So for example, does setting the position property affect how other properties like left or top are interpreted? But it turns out that not only is there no kind of formal mechanism for reasoning about dependencies of properties, there isn't really one for reasoning about entire modules of properties together. So this graph here was a one-time effort in 2005 and represents the last known attempt to identify dependencies between CSS modules. So for example, it's hard to see, but this CSS3 box model pertains to properties like top or padding and margin and border and height and width, whereas the selectors module refers to the grammar for how a selector is constructed for a rule and so on and so forth. And so this is kind of just like a visualization to show the complexity at a very, very high level, not even on the level of individual properties. But as to why we would care about this, consider this example snippet from the box model specification. And note that this snippet that describes the algorithm is currently a proposed annotation, not even a part of the formal specification itself. So this outlines the rules for how the browser agent calculates the display value of an element. And you can see that it's pretty complex. It's like a decision tree. So if display is none, then we ignore the float and position properties. Otherwise, if position is neither static nor relative, and so on and so forth. So here we have a kind of combinatorial result that is a function of three different properties: display, float, and position. And all of those go towards determining the computed value of the display property. Here I've drawn a kind of graph that shows what it would look like just between the display position properties and then properties like height, width, z-index, top, left, and bottom. So I guess the way to interpret this is for the display property with potential values of none, inline, block, inline, and block, and I'm aware that this is only a subset of the possible values. Inline and block affect width in the sense that inline causes with setting an element to display inline means that we don't care about the value of the width or the height, and so we ignore those things, which is what the X denotes here. And likewise, in the default positioning value of static, we don't care about things like z-index or top, left, bottom, right, so on and so forth. But setting the value to, say, setting the position value to like fixed, relative, or absolute means that we do care about and interpret those particular property settings. So this kind of shows what we would like to be able to teach people. Obviously not by showing them this entire graph at once, which would be really overwhelming, but describes the kind of semantics and hierarchical organization and relationships between properties that is not made clear from existing tools. And so we can now kind of talk about what those problems are. The motivation and argument behind our departure from current state-of-the-art inspection tools like Chrome DevTools, Firefox developer tools, is that those tools don't represent CSS in a way that conveys the relational and combinatorial semantics of how browsers interpret the written style sheets, which means that users leave with inaccurate mental models. So, for example, if we look at, here's an example of inspecting the website for the sort of lorem ipsum generator. So it's kind of a nice website, not too complex. But if you pay attention to sort of the CSS display here, you can see that properties are shown kind of one-dimensionally and in disjoint sets. So this is one set, this is one set, and so on and so forth. And that sort of incorrectly gives you the idea that each of these properties has an equal level of precedence, and that they are all sort of, that setting one property alone has some effect and some other property, has another effect, and then when you compose them, you get this effect, in this sort of like sum total effect. But what actually happens is, for example here, setting the value of display flex is what causes flex and flex wrap to be computed or looked at. And if you were to disable that, suddenly it doesn't matter what you set flex to or flex wrap to, because the element itself does not have a display setting of flex. And so here you have this implicitly hierarchical relationship between properties that is not well conveyed by this very one-dimensional display format. And so what we would like to do is allow users to simultaneously inspect, first of all, multiple elements, because oftentimes there are properties that depend on settings of the parent or ancestor element somehow, and because you can only inspect one element at a time in the current dev tools, it's not very clear how to show people those properties and the relationships that are, the dependency relationships involved. And second, we would like to be able to show people the individual properties kind of organized hierarchically according to the dependence relationships that are shown, for example, in this graph, where the value of position affects the whether or not we care about the value of the top property. Rather than just showing them all sort of in one line that implies they have equal precedence. And so an example of what we might want to look at is, this is not an example of the visual interface that we would want to achieve necessarily, but it does show kind of the semantic effect. If you have a position value of relative, then you have these properties z-index and top, you want to show here that having this relative value means that we care about the values and settings of z-index and top respectively. If you change that value to static, then this is supposed to be kind of a lighter color, but it shows that we don't care about those values, and those paths are sort of not active at all, because this value here sort of serves as a blocker that means that stops the browser rendering agent from investigating what these properties mean, because they're not relevant to a statically positioned element. So our research questions are as follows. How might we apply instructional design principles to building a web inspector designed for sense-making? This question sort of borrows from a lot of Quintana's work on creating software for science exploration and sense-making, and the design principles that are involved to help new users kind of come to terms with the difficult disciplinary semantics of a new science principle through exploration. The second research question we have is, how might we visualize information to convey CSS semantics and expose hidden state? By hidden state, we mean these properties, the settings of these more abstract properties like position that don't directly translate to a concrete effect on the page, whereas a property like top does translate into a 10 pixel shift in the user's mind. And the position property is kind of hidden in the sense that it doesn't have a effect by itself, and it doesn't have a effect that is easily sort of represented through some visualization, but it does set the state for whether or not these other properties that sort of depend on it are interpreted at all. And so this is the same problem that a lot of people try to struggle with when they teach people imperative programming, where there is a mutable global state that affects how functions evaluate. And so we want to kind of start to apply that to web inspector design, which isn't really a direction that people have gone in before. We conducted a survey in DTR of students who had significant amounts of independent developer experience. Many of them were also TAs for EECS 330, which involves teaching CSS to a small extent to the students. And we overwhelmingly found that users don't think about how CSS really works and consider positioning and layout algorithms to be a black box. People repeatedly referenced a process of trial and error where success did not necessarily correspond to increased understanding, mostly just like a successful combination of properties copied from Stack Overflow and adjusted until the visual outcome sort of matched what they had in mind. We also came to the realization that users can understand and reason about properties with a clear concrete effect, but they don't understand the hidden state properties that we previously talked about. So for example, consider this snippet of CSS, right? You can say, okay, the top 50 pixel property has a very concrete translation into a effect on the page, but there's no real clear mapping for what position relative means. And on top of that, another aspect of the positioning semantics that isn't sort of present here is that setting an element to position relative makes it relative to its closest position ancestor. So here we can see that if another part of the style sheet has this selector that applies to that element's parent, that setting position relative on the parent means that the child is positioned relative to the parent. But because you can only inspect either the child or the parent in current tools, there's no real way to make this relationship clear. We developed a system called Perseus. I've called it Perseus for 3 reasons. The first reason is that it has Percy, like perception or something like that, in the name. Second reason is that there's already a precedent for systems in this space borrowing names from other systems, so Web Crystal, Fire Crystal, Perseus, Theseus. The third reason is because Perseus in Greek mythology is responsible for slaying Medusa, and CSS is a lot like Medusa. So the main system affordances that we have developed so far are a DOM inspection, an isolation panel that's designed to decrease the amount of information overload a user has when they are going to inspect a given page. We've also implemented the ability to inspect multiple elements at once so that users can see these relationships that we've described above between the child and the parent. And so to kind of give a walkthrough of what that system looks like. So for comparison, we're going to be inspecting this whole region of the page, and in particular, we're curious about how they've gotten this kind of large image behind the rest of the text, coupled with these decorative SVG elements here. So I'm going to inspect that. Okay, so here we have this this element corresponding to this region of the page. And we can expand that and see all of the different pieces that are inside of it. If we wanted to look at how our system works, so there are a couple pieces of our system. The first piece involves a socket server that we can start up. And this will basically serve as a proxy server that allows for our Chrome extension here to publicize information about private Chrome developer APIs to any arbitrary system that we would like to connect. So here we've set the extension to start debugging this particular page. And now, if we go to our system, you can see here that it serves the request for styles. This is our interface for inspecting a new subtree of the DOM. And so you can see here right off the bat that it is, we've designed it so that you can if you're inspecting this subtree here, you don't care about any of the surrounding context yet. And so what we would like to be able to show people is the isolated child of that particular tree. And the second thing we've done here is make the expansion breadth first, So instead of sort of showing everyone like the entire subtree all at once, which can quickly lead to a lot of information overload and content, we want them to be able to control the rate at which information is shown by expanding things individually and checking to see whether there's anything of interest in that particular view. A couple of other small affordances we've implemented in this particular part of our app. First, with a property that with a tag that has a single child, which is a text value. So this heading file that begins with hedonist roots for some reason. We want to be able to show people the, here we go. We want to be able to show people the value in line, just like we have in the regular inspector. But for example, consider this block quote here, right? This block quote says, "Nor is there anyone who loves or pursues," so on and so forth, and that corresponds to some element on the page. And here, you would need to expand the block quote elements to be able to see the content, but this is not only more work for the user, and it also takes up more screen real estate, which is actually very important when you're trying to decrease the amount of information presented at any given time. And so by minimizing the amount of work people have to do, by expanding elements that are just clearly going to be false leads and not relevant to what they're looking for, we allow people to sort of get in and get out and find what they need more quickly. The second kind of small design consideration that we had was to show elements in kind of a ordered list, or unordered list type format, where instead of showing both the start of the tag and the end of the tag, we only show the start of the tag because that's what matters. This has the effect of making any given sort of element on the page take up half as much space in the inspector because you don't also have to show the concluding tag. And so this means that we don't end up with situations where you have just like lots and lots of singularly nested tags. There's not a good example here, but if you had a container with a child and a child inside of it and a child inside of that and so on and so forth, you would end up with something that was like pretty messy and had this sort of large in-cutting indentation, and then it would go out, and you would have all of that space taken up just to show what was really like a single element that you cared about. So suppose we want to understand how these pages squiggles work, right? And here we can see that by expanding here to show the squiggles, you can select multiple elements at once. So here we've selected the root, parent root, the GR, the grid cell, as well as the page selection squiggle. And we can see the computed styles that we care about for the parent here and the child here. And so the first thing we notice is that this particular child has a position value of relative. And we didn't finish implementing a lot of the CSS visualizations we wanted to, but this is sort of a proof of concept that demonstrates how you can understand relationships of properties that require you to see multiple elements at once, where you can't do that at all in the current inspector. So by noting that this property position value is set to relative for the squiggle, we can say, okay, what is it relative to? So if you wanted to take a look at the parent fig caption, that one is static, which means that it doesn't serve as a positioned ancestor, which means that the next closest ancestor is this grid value, and you can see that that's also static. What this allows us to do in further iterations of our tool is to demonstrate that because this element is relatively positioned, but none of the properties that we normally use to adjust the position are set, that means that it likely serves as a positioning context for a child that is positioned relative to the current element. So we don't care about that element anymore, and now we're only looking at this squiggle container. If we expand that and take a look at its children, say squiggle 1, we can see that this element is positioned absolutely, and that it has offsets for the height and bottom properties. And so now we can see that it's positioned absolutely to this parent, which is relatively positioned. So that's why we didn't have any settings for top, left, right, or bottom here. And this is sort of an example of the combinatorial aspects of CSS that we can see with this particular system that we can't over here. If we look at the aforementioned sort of page section squiggle, and we see the position relative property here, if we want to take a look at what the children are, we would lose focus on the parent. And so you can see this is position absolute, but you would sort of need to toggle back and forth between the parent and the child, whereas our system makes it very clear what the relationships between those properties are. Or rather, it doesn't make it clear yet, but it allows you to see that. And in future iterations, it's sort of just a question of like creating the appropriate designs to be able to bring people's attention to this relative setting and this absolute setting. A little bit about the tech that we're using here. So as previously mentioned, we have a Chrome extension that sort of publishes information about the browser's rendering, layout, and CSS computations to our application because we didn't want to have to develop within the Chrome extension ecosystem necessarily. We have a socket.io server that serves just forward requests from the client as well as responses from the Chrome extension. And then we have this application is done as a React front end. And that allows us to do pretty nice state management where you can just have a global application state consisting of the currently inspected DOM tree as well as pointers to the nodes that matter and the children here. And then you have, or rather, not the children, the styles, but then you can just pass down that information to UI components of the subtree, and it manages sort of the re-rendering of that. The big tech accomplishment for us this quarter was that our system works to debug arbitrary targets. So this is not a terribly complex web page, but it is sort of an example of an arbitrary third-party website that someone would like to inspect. And because our sort of broader goal pertains to authentic learning from professional websites of personal interest, it was very important that we not just limit the realm of possible inspectable targets to a set of kind of toy examples that had been curated ahead of time. We didn't get a chance to do a ton of work with the study because we didn't have the necessary tech to implement like kind of the CSS state visualizations that we wanted to show, but I can kind of outline what that would look like in the future. And that's sort of going to be what I want to do at the start of next quarter. So this pertains to the vertical align property, which kind of misleadingly suggests that you can align an element to the middle of its parent context, but actually requires an element to have a display value of inline block or table for historical reasons, apparently. And so we would like to be able to show people that the value setting of display controls whether we care about the properties height, width, and vertical align, and in particular, when you have display block set, vertical align, this is supposed to be written kind of in a lighter color, but we don't care about vertical align at all. And that moreover, when you set something to display inline block, for instance, this is a bad example because it doesn't illustrate that, but when you set something to display inline block, the height value is automatically corresponds to whatever the line height property is. And so we would like to be able to show people kind of how those two properties relate given the selector or given the surrounding context or state. We would also like to show people kind of a better, more concrete example of what I illustrated with the position relative, position absolute example just now, which is that if you have an element set to position relative, but none of the adjustment properties that would depend on relative are set, then it likely constitutes a positioning container for its children. And you can see here, on the other hand, that if position relative is set and there's an adjustment property, then suddenly we care about the position ancestor and we can show the user what that position ancestor would look like. And all of this information is accessible given the kind of back-end infrastructure that we currently have. We just haven't implemented the visualizations. Of course, it's a lot harder to think about how this would expand past just a simple subset of properties related to position and display. But that kind of challenge of tackling just how an element is sized and positioned would represent a lot of the struggles that people currently deal with when they try to understand CSS to begin with. All right, thanks so much.